Hi everyone, thanks for joining. My name is Fahad bin Tariq and I am the track lead for public key infrastructure, data security, and online fraud prevention at Systems Limited. So I have overall 20 years of work experience. 16 years of those were in Germany and the last 4 were here in Pakistan. So some highlights of those 16 years are having worked for 7 years in the field of digital identity, as well as being the architect for software that was written for Volkswagen and Volvo trucks, as well as working on the digital health rollout of the next generation of Germany's health infrastructure that was commissioned by the Ministry of Health. So our topic for today is establishing trust in a digital world. So what is the importance of trust? Trust makes the world go round, right? So we rely on trust for everyday actions. If we want to communicate, if we want to go from point A to point B, if we want to pay for a service, every aspect of our life depend on trust. So it's safe to say that everything is based on trust. So let's take a look at a real life example. I think most of you have visited a bank branch before. I know I have. So when I visit a bank branch, right? So the trust is implicit. I know the location of the branch, right? I know that this is a genuine branch. The people sitting there are most probably genuine employees of the bank who want to serve me as their client. There are forms over there that I fill in, right? I use their ATMs, I use the cards that they give me, okay? And I trust them with my personal information and my finances. Similarly, the bank wants to identify, wants to trust, wants to know that it's really me. So they check my ID cards, they check the signatures on the checks that I provide. So basically the trust is mutual. So let's look at a few scenarios, examples where trust is a problem. So let's say that you want to communicate with a person, call them A or Alice, whatever you want, but you can't see them, right? So there's a barrier, there's a wall between you and A, okay? And you want to exchange messages, so you can send messages through this barrier, through this wall, send and receive messages, but you have no way of finding out whether it's actually A on the other side who is receiving and sending the messages. So the problem that you have here is one of identity. Let's take this scenario forward. So it's a similar situation. You want to communicate with A, they're behind a barrier, you can't see them, but this time you're not communicating directly with them, but there are multiple hops, multiple people in between. So every message, every package that you send to A gets transferred from hand to hand by these multiple people, right? So the problem that you're facing now is that you have no way of ensuring that no one is actually tampering the messages or the packages that you want to be delivered to A. Similarly, the response that A is giving is that what A wanted to send back to you. So let's say even magically, if you somehow find out that that is actually A on the other side, you have no way of guaranteeing that these messages in between are not being tampered with. So this is a problem of data integrity. And finally, let's take a look at a third scenario. Let's say, so we have the same scenario, you want to talk with A, there are multiple people in between. Let's say you somehow solve the identity and the integrity problem, but right now you don't want the people in between to be able to understand the data that you're, or to understand the messages or packages that you're sending to A. Why? Because you may be sending your credit card information, you may be sending your personal address, and you don't want the people, unknown people in between to understand that, right? So the problem that you're facing here is of confidentiality. So in these scenarios, in the absence of trust, would you be willing, so you should ask yourself, would you be willing to share your sensitive data? Would you be willing to pay money to a service that you don't trust? Would you be willing to send or receive packages that may be tampered with? Or, basically, would you even be willing to communicate with an identity, with a person whose identity you are not aware of? So the answer to, I think, safely to all of these is a resounding no. So now the question is how to establish, ensure trust in a digital connected world where we want instant services from people, from organizations who we have no idea about. So you may ask, is this website that I'm visiting, is it authentic or am I being scammed? How do I know that my data is not being recorded by malicious actors in between? Can I trust the update packages? So let's say you have an electric car, right? And you get an download package. How can you trust that this update is genuine, right? If it's not genuine, if it's malicious, it may lead to a crash of your car. So the list goes on, right? There are other examples. So if you're software developers, then you may, deploying software on servers, then you may be asking, okay, so you have a development team developing software. How do I know that the software that is actually being deployed on the servers is the software that they wrote, is the software that they compiled, right? Has it been replaced or has it been tampered with in between? So these questions, they go on, right? So now, coming to the answers. In a digital world, there are basically two things that are used to resolve the issues of trust. The first thing is public key cryptography and a setup based on public key cryptography called public key infrastructure. So let's decode what are these things. So first of all, starting with public key cryptography. Here you have an asymmetric key pair. So basically, what is an asymmetric key pair? The generation process gives you two distinct keys, and these keys have some mathematical properties, right? So first of all, they're not just two random distinct numbers. They are basically a pair. That means they are related. They're separate, but they're related. Secondly, they act as a trapdoor function. So what is a trapdoor function? A trapdoor function is a one-way function. So just imagine you have a trapdoor and you walk through it and it shuts down behind you, so you can't go back. So basically, how are they related? How are these keys related? So if you take one of these two keys, right? You take the first key, use it to perform an operation. To undo the operation, to reverse the operation, you can't use the same key. You need the other corresponding key of that key pair to undo that operation. So that is how they are related. That is why they are called asymmetric. So when you have these two keys, one of them is kept private and the other can be shared with others, and that's why it's called a public key. The public key is used to encrypt the data, and that is why this is called a public key cryptography. Why is it secure? Because these are really, really large numbers, and to break them would require even supercomputers, centuries, current supercomputers. So having such an asymmetric key pair with one public and one private gives rise to some wonderful capabilities. And this basically creates the backbone to solving all of the issues that we had in our scenarios. So what does this all mean? So the basic concept is that everything that requires an identity is given such a key pair, right? The private one is kept secret, the public can be shared. So a person, a server, an internet domain, or let's say a device connected in an IoT network, all of these, if they need to have an identity, are given a key pair. Sounds easy, but in the practical world, this raises some more questions. Who will generate the key pair? Myself or a third party? Where will the private key be securely saved? What should be the length of the key, right? What algorithm should I use? You may have heard of RSA or elliptic curves. You can Google that. When should the keys expire? What happens when the keys expire? What happens if the private key is found? So there are many such questions that have to be answered. And that brings us to the second component, right? So now that we have a strong mathematical basis, we need a setup that provides us processes, roles, a hierarchical structure between those roles, and some artifacts. And that is provided to us by public key infrastructure. So once you have both of these components, public key cryptography and public key infrastructure in place, then this results in guarantees for data integrity, secure communication, authentication and digital identities, non-repudiation, and so on. So let's revisit the example, the first scenario that we saw where we just simply wanted to communicate with A and there was a barrier in between and we had the problem of identification. So before I start exchanging my data with A, I'll ask them to provide their public key to me, right? So I get a public key, and normally it's wrapped in a container called a digital certificate. You may have heard of that. So you get that certificate, but still there are two issues. How do I know that this certificate or this public key actually belongs to A? There may be an imposter there, and they're claiming to be A, and they send me their public key. So that's where the public key infrastructure also plays a role. You have certificate authorities or any authority that vouches, that says that, yeah, okay, I guarantee that this is the key of A. Okay, so that is one problem solved. I now have the public key of A. But do I still know that it's actually A on the other side that sent me this key? Or maybe it's still an imposter who had access of A's public key because, as you know, the public key is public, anyone can have it. So what I do now is I go back to the mathematical relationship between public and private, right? So what I do is I take A's public key and I take any number, a challenge or a sentence, anything, and I perform an operation using A's public key, right? This is called an encryption operation. I encrypt this and the result, the encrypted package, I send over to A, right? So this is a challenge now for the person on the other side. I'm saying that, okay, if you're claiming to be A, that means you have the corresponding private key. And since this is an asymmetric key, the operation that I perform using the public key can only be reversed, or the challenge, the encrypted challenge, can only be found out if you possess the private key, right? So who will possess the private key? Only A or Alice or whatever, who I wanted to communicate with, can have the private key. So if they successfully can decrypt the challenge, that means I'm actually talking to A. So that solves my identity problem. So you may also be asking, where else is this used? So this is actually what happens every time your browser or your app connects to a service. Google, Instagram, Facebook, your bank, anything. Even right now, when you're on this live Instagram session, you have public key infrastructure, you have keys at the back who have made a secure connection, and that is how your app, your phone knows that it's actually talking to Instagram, right? You can Google the importance of TLS. So in fact, the vast majority of communication done via the internet is done securely thanks to PKI. So once you have the basis for establishing trust, right? Once you have this PKI set up, then the possibilities are endless. Governments can provide digital services to their citizens where mutual authentication is required. So you need to be sure that that's actually a government service. The government needs to know, okay, this is actually my citizen, right? You can have mechanisms to provide digital signatures for e-contracts. So instead of going to notary publics, instead of using stamp papers, instead of having to run around with signatures, you can use digital signatures. In fact, a topic nowadays, electronic voting can also be made possible using public key infrastructure. And coming back to our software developer example, how do they make sure that there is no malicious code being loaded into their deployment servers? Well, the concept used there is called code signing, right? So you have special keys, you have these the corresponding key which signs the code before the package is delivered, right? And then before the server deploys it, it checks the signature, it checks, again, using the public key, it checks, okay, is this actually a valid signature or not? If it's not valid, that means something fishy has happened in between, it will reject the software package. And if everything is fine, then you know that actually came from the correct source. Similarly, you can have multiple use cases. You can have banks that provide services without requiring your presence or your biometrics. So, so a question that you may have here is that if public key cryptography, public key infrastructure is so secure, if it's so effective, it's so good to establish trust, why do we still use username and passwords to authenticate ourselves, to identify ourselves? And that's a very valid question. Ideally, we wouldn't be using username and passwords, and that is what an alliance called FIDO, Fast ID Online, is working towards. So you've got all the major players or all the major companies. Again, you can Google it for the details. So you may have seen when you go to Google that it's actually offering you a new way to sign in, and that is called passkeys instead of passwords. So what are passkeys? Passkeys are actually nothing else but an asymmetric key pair that is generated on your device, on your laptop, on your phone. The private key is securely saved there. The public one is sent to the server, Google or whatever, right? And the next time you want to log in, you simply swipe your phone, you give your fingerprint, or your retina is scanned, and that unlocks the private key on your device, which is then used to log into the service, right? So this not only provides better user experience because you don't have to, write usernames and passwords. You don't have to remember anything, no OTPs. You simply, swipe the phone as you do multiple times a day, and you're logged in, right? And at the back, you have public infrastructure, so you know that at the back you have something with strong, secure foundations that is ensuring a secure connection, secure authentication, secure identity. So let's talk about some challenges that we have today, and why I'm actually doing this session. So although public key infrastructure is not that new, but its adaptation, its importance still has not been understood. So you have people in top management that are unaware of its importance. So they know that, okay, they may require a digital certificate that has to be placed somewhere, but they don't have answers to the questions that who should generate these certificates, who will be the owner of the root key, what happens when the certificate expires, what algorithm to use, and so on. So actually in the world, you have even less than 38% of organizations who have sufficient staff dedicated to have a proper public key infrastructure deployment. And this leads to potential mishaps and security breaches. So finally, one interesting question that you may also have is, you may have heard of quantum computers. So I'll just quickly, I know time's up, I'll just wrap this up. Will quantum computers have an effect? The answer is yes and no. In the near future, they won't affect public key infrastructure as we know it, but eventually they will, because quantum computers solve problems exponentially faster